welcome everybody. So before I go further into concluding our sum of series in sigma notation and also exponent in the variable, we're just gonna do this question which someone commented that wanted to be done under mathematical induction. All right, so the question was that suppose prove that the sum of any terms is given by n open bracket n plus 1. Then the first term is given by that. So what we're proving is just the sum. Yeah, the sum which is here. So like I said, our first step you let your Pn. Now in this case, you're just gonna get the same thing which we're having. So let me not even write that one. Then you go to the second step. Your second step, you just calculate, solve for n is equal to 1. So why I've used n is equal to 1, that in this case we've not been given on a restriction as such, but it has only been given that for all positive values. So all positive integers, you can start from 1 or 2 or anything. So S1 is equal to 1 open bracket 1 plus 1. Then S1 is equal to 2. Then from there we have A1 is equal to 2 open bracket 1. So A1 is equal to 2. And you agree with me, if you only have one term in a sequence or maybe, yeah, on a line, you only have one term, the sum of that one term will be the exact term. All right, so this is what we have. Then the third step, you assume for n is equal to k, our statement sk is equal to k plus 1. And we have a of k is equal to 2k is true. So these statements are true. All right, then our fourth step we prove by induction that since for n is equal to k, the statement is true, then this holds that for n is equal to k plus 1 term, it will be true. Now we need to prove that one by induction. So we replace, so k plus 1 is equal to k plus 1 open bracket k plus 1 plus 1. All right, so that is what we're having. So I can say sk plus 1 is equal to k plus 1 k plus, that's a 2. All right, now from there what we do is very simple. We now get our sk. Yeah, so we now get our sk from here. All right, so we get our sk from here, and also we get our 2. Now from there we also write for ak plus 1, equals to 2 open bracket k plus 1. All right, so what we do now, we just need to get our sk. So we say s of k. Yeah, so s of k. So since we know that if you have one term, the sum of that term will just be the same exact term. So what we can do here, we can get the sum of k, which is one term, the sum of one term, which is k, plus sk plus 1 is equal to k plus 1 open bracket k plus 1, then plus 2. All right, now our sk, so what you can get our sk in this case, we'll get this one here. So we'll get this one and this one. Since this side we have this, so we'll get this one, our sk, which we're having there, k plus 1. Let me say open bracket k plus 1 plus. Now for our sk, we'll replace it. Since in our first statement to say these two, they will give the same things, so we'll get this one. We'll get 2k plus 1. All right, equals to k plus 1, k plus 2. All right, so there what we are having, if you look at this, these are just factors. So the factors, we can get them k plus 1, open bracket k plus 2, then equal to k plus 1, k plus 2. All right, then we're all done. Settled. All right, now let's go straight into sum of series under sigma notation. Sum of series under sigma notation. So sum of series sigma notation. All right, so suppose we have an example. So in our example, we are saying prove that n to r plus 5 is equal to n open bracket n plus 6 close bracket. This is a 6. All right, yeah, there we have it. Hope everybody's able to see that. Okay, so what we do now from here, we just let our first step Pn be such that n r equal to 1 to r plus 5 is equal to n plus 6. All right, close bracket. Then from there we prove for n. Now in this case it was just for all. Sorry, I forgot to write that one. Let me put it here. This was for all values of n positive integers. So we might have maybe natural numbers, something like that. It's also one and the same. All right, so P1, so step 2, P1, such that 1 r equals to 1. Now 2, 1, where there's r plus 5 is equal to 1, open bracket 1 plus 6. All right, so what we're having here, so on the left hand side it's 7 and on the right hand side we have a 7, right? All right, then step 3, we assuming n equals to k is true in the statement. So where there's n, we replace by our k. So r equals to 1, open bracket 2, r plus 5 equal to k, open bracket k plus 6. All right, there we have it. Then from there, what we do, we go to our fourth step. So this one you write is true. Always the step, our third step is always true. So fourth step, now you prove by induction that n equals to k plus 1 is true. So you replace where there's n by k plus 1, r equals to 1, 2r plus 5 is equal to k plus 1, k plus 1 plus 6. All right, so what we are having now, what you do is you add these two terms, your k and your k plus 1. So when adding now, I'm saying you add k, summation of k, r equals to 1, plus the summation of k plus 1, r equals to 1, is equal to 2, it's equal to k plus 1, k plus 7. Let me put it 7 here. Then, so our k plus 1, in our statement, our k plus 1 from our assumption, it's this one, k. So we have k, open bracket k plus 6. Then plus this one. Now what you do, you replace now, for this one, you replace where there's r, you put k plus 1. All right, so you say 2 k plus 1 plus 5 is equal to k plus 1, k plus 7. All right, then if you look at this, what we're having here, if you expand them, this will be k squared plus 6k plus, this will be 2k plus 2 plus 5. This is equal to k squared plus 8k plus 7. All right, then this one is k squared plus 8k plus 7 is equal to k squared plus 8k plus 7. All right, then you are all done. Everything is settled just like that. All right, now having looked at sum of series under sigma notation, we're just now gonna go lastly look into some exponent in the variable problem types. So it's a proof 2n greater than or equal to n plus 4 for all. So this one, they've given a condition for all n natural numbers where n is greater than or equal to 3. All right, so our first step you read. So our first step can say bn such that 2n greater than or equal to n plus 4. Then our second step, you solve for n. Now in this case, n has been restricted to all positive natural numbers going from, numbers greater than or equal to 3. So you can use 3. All right. So 2 power 3 greater than or equal to 3 plus 4. So this is 8 greater than or equal to 7. And this is true. Is true. All right. Then our third step, you just assume for n is equal to k, in our statement 2 power k greater than or equal to k plus 4 is true. So this one is always true. Then our fourth step. Under our fourth step, what we do there now is we prove for n equal to k plus 1. So since this is true, then this holds that for n is equal to k will be true. Now we need to prove it. Using mathematical induction under induction synthesis. So what you do, replace 2k plus 1 greater than or equal to 4. Greater than or equal to k plus 1 plus 4. So here if we go under indices, in indices you agree with me, this will be 2k multiplied by 2 power 1 greater than or equal to this will be k plus 5. So this one, 2k plus this one, we are in here, we said if we assume n is equal to k, then 2 to the power k is greater than or equal to k minus 4. And you agree with me, if this is what I mean, then k is either equal to k plus 4 or k plus something bigger than k plus 4. So in this case, we're just going to take that k plus 4. K plus 4 plus 2, was it times 2? Sorry. Yeah, times 2 greater than or equal to k plus 5. So if you multiply this one, this will give you 2k plus 8 greater than or equal to k plus 5. And this is true. Whatever value that you put in, this will be true. All right. So this is where we end with our mathematical induction type. And if there's any question, just write in the comment box below. And don't forget to subscribe and hit the notification button so that whenever there's a new video, we'll be able to notify you. All right. Thank you very much. Have a good day.